All right, hello everyone, hope you're doing well. Today is going to be a video lesson about nuclear reactions. We're going to be going over nuclear fusion and nuclear fission. So our objective for this lesson is we'll be able to develop models for nuclear fusion and nuclear fission through nuclear equations, and also related to the conservation of energy and mass. All right, in the universe, there are 4 fundamental forces. We already went over half of them, and we also slightly went over the other ones. They are gravitational forces, so the force of gravity, like you see right here with the sun and the earth. Weak nuclear forces, which we'll talk about in another video, and it has to do with decay. Electromagnetic forces, which has to do with electricity and magnets. So what we talked about for, remember, the cell phone project and stuff like that. And finally, strong nuclear forces, which we're going to be focused on today. Strong nuclear forces are the most strongest type of the fundamental forces, and it's the force that binds nucleus or nuclei together. So this is what how nuclear reactions take place. So you can see here is an example of a strong nuclear force of 2 elements combining together to make to fuse together to make a new element. We're first going to talk about nuclear fusion. And nuclear fusion is when 2 nuclei come together to form a single nucleus. An example we're going to talk about is like 2 isotopes of hydrogen that are fusing together to form helium, which happens in the sun. Now this is different from other standard chemical reactions. In other reactions, we usually have the electrons between atoms or molecules either shared or remove electrons, but this is not the case for nuclear reactions. For this case, the 2 elements or molecules literally combine together to make a new product. So I have 2 examples here. The first one is what I mentioned before. 2 hydrogen atoms are fused together to make helium. This is a standard hydrogen atom. And this is another hydrogen atom. This one has a proton and also a neutron. And this one has 1 proton and 2 neutrons. We can see here from the green. These are not stable by themselves, so that's why they want to fuse together to make helium. And also there's another neutron left over. As you can tell, the numbers on top are always equal on both sides of the equation. 2, 3, that's 5 total. 4, 1, that's 5 total. All right, now let's look up here. You see that 2 helium atoms are fused together to make beryllium. Like again, 4, 4, 8. These are balanced on both sides. And same thing here, the beryllium from here is combined from helium in order to make carbon 12. 8, 4, 12 equals 12. So there's 2 atoms combining together to make another new element. So let me show it step by step. So right here, like I mentioned, we have 1 isotope of hydrogen with a neutron and a proton, plus another isotope, equals helium, and another neutron. The 0, remember, if you remember here, the bottom number is the number of protons, so 2, the atomic number of helium, and the top number is the number of protons and neutrons. So 2 protons, 2 neutrons, 4 for helium. All right. So this is what happens. So we're going to have, that's the H2, and it combines with the H3 to make the helium. So this is the helium, this is the H2 one, this is the H3 one, and we're leave with an extra neutron. This is the end. So these 2 are literally combined together, but leave another neutron. This is where just the energy is released. Right? Now let's talk about nuclear fission. This is the opposite of nuclear fusion. Instead of two atoms combining together to make a single element, this is where one element splits into two or more similar sized nucleus. So we usually eject a neutron or an alpha particle, so helium atom, to a larger element, and it causes them to split into other atoms. A common thing we use it for is uranium. And that's a common element used that we use for nuclear power plants. And nuclear fission is what we use to power nuclear power plants, because there's usually a lot of energy released. So here's an example of uranium. We have a neutron being injected to a uranium-235. And we see here it becomes barium-141 and krypton-92 with 3 neutrons. These reactions will usually be given to you. It just depends on what isotopes we have and how it turns out. If you notice 235, if you add 141 and 92, you will get the same thing, 235. Well, 141, 192, and 3, and 3 times 1. So the masses need to be the same. Well, not the atomic mass. The number of protons and neutrons needs to remain the same. So let me show it step by step. So we have a uranium 235, I'll just say U-235. We have a single neutron that's being injected to it. This becomes uranium-236. And when it has that extra neutron, it's very unstable. So it's going to want to split into different elements. That's why, in order to be stable, it becomes the barium and the krypton, plus 3 neutrons. These elements are more stable because if it was, the uranium does not naturally want to be at 236 protons and neutrons, so it wants to be in a more stable format, and that's why it ejects itself to barium and krypton. Now the 3 neutrons, that releases a lot of energy from the nuclear fission reactions, and this is what we use for power. All right. Now there's a problem here. The number of protons and neutrons are the same, but if you actually look at their masses, it's actually going to be something different. So uranium-236, when we add that neutron, has a mass, and we're talking about atomic mass units, 236 point all of this. Barium-141, it becomes 140.9144. Krypton-92 is 91.92, etc. And the 3 neutrons, their masses are 3.025995. And this is the total before it splits. And then when we look at the total after it splits, it's 235.867. They're not the same masses. So I know I mentioned that the numbers on top of here are supposed to be equal, but that's for approximation. But actually, for nuclear reactions, mass and energy are not entirely conserved like how you'll think in other reactions. But there's a reason that they're not conserved like how you'll think of other chemical reactions, other parts of physics. And this is actually discovered by Einstein himself, and you'll probably know of his famous equation. Mass can be transformed literally into energy, so there can be a loss of mass for nuclear reactions. But that mass is transformed into energy. So this equation to solve this is, you've probably heard of this equation, E equals mc squared, where E is the energy, m is the mass, and c is the speed of light squared. Einstein discovered through nuclear fission or fusion that mass can be transformed into energy, and that's how it conserves both energy and mass mathematically. The mass becomes energy, so both are conserved, And like I mentioned before, there's that extra mass for the uranium. This is about like this is around 0.14 or about 0.2 points apart. That 0.2 AMU just can lead to a lot of energy that we use for nuclear fission reactions. So yeah, the equations we went over, nuclear fission, where a big element splits into 2 or more elements. And then nuclear fusion, where 2 elements combine to make a bigger one. And then energy and mass is conserved through the equation E equals mc squared. You don't have to do a calculation for this, but it's just for you to see how they are related to each other. All right, that's it for this lesson. Next lesson, we're going to be going over nuclear decay. Hope to see you then. Oh, I almost forgot. I have a little game for nuclear fusion. This is a link I provided to you in Schoolsheet, but I'll also put in the description of this video. This game is just like 2048. If you remember that game, we had to put the numbers together to try to reach 2048. This is similar, but instead we're trying to do it to make iron 26. Below has like some fusion equations: hydrogen, hydrogen, deuterium, hydrogen, helium, etc. All of this, and just to see if you can try to make the iron 26. You just move with the with the keyboard up, down, left, right, and just try to play it until you reach iron 26. So some of you try this and see if you have fun with this. All right, bye.